All right, now we are in row reduction, methods, and terminology. So last time we discussed how to represent systems of linear equations as matrices and used elementary row operations as a tool to solve a given system of equations. Row operations corresponded to manipulating equations in a mathematically correct way. For example, if you had A equals B, C equals D, that's equivalent to A equals B, A plus C is B plus D. We can get both of these pairs of equations from each other. So in this chapter, we introduce more terminology and some historically important tools for solving systems of equations this way. So the tool is Gaussian elimination. There's a few ways to use matrices in order to solve systems of linear equations. We'll see a table below. We'll completely reduce a 3 by 3 part of the 3 by 4 augmented matrix to the identity matrix, obtaining, actually that's a typo, we'll obtain something else. But this kind of matrix with identity on the left side of this divider, we'll see soon. It's an example of an augmented matrix in reduced row echelon form. So let's define what that means. And in this case, our equation will have a unique solution in reduced row echelon form, which isn't always the case. So generally, an augmented matrix is in row echelon form if it satisfies all rows have zero entries in A, having zero entries in A, are at the bottom of the matrix. The leading entry, also called the pivot of each row, which is the leftmost non-zero entry of each row of A, is to the right of the leading entry of every row above it. We will see in the example below. Not all rows have a pivot. For example, 0 rows of A don't have non-zero leading entries. We'll see some examples. So the matrix is said to be reduced to echelon form if it in addition satisfies the pivots equal 1, and each column containing a pivot, that's 1, has zeros in all other entries. That's for the columns. So not necessarily the rows. The rows don't all have to have non-zero entries in reduced to echelon form. We'll see an example too. So if you have the identity matrix, then already the augmented matrix AB is in reduced row echelon form. So why is that? Let's draw a picture. So if I have like 1, 0, 0, 0, 1, 0, 0, 0, 1, anything here, maybe it's just a column, maybe it's more than one column, then all rows having zero entries are at the bottom. Well, there's no zero entries, so that doesn't apply. So that is true. The leading entry of each row is to the right of the leading entry in every row above it. So in this one, 1 is to the right of every row above it. There's nothing above it. In this one, it's to the right of the pivot above it. And this one is to the right of the one above it in the second row and to the right of the first row. So it's in row echelon form. It's also in reduced row echelon form because the pivots are equal to 1. And each column containing a 1 pivot has zeros in all other entries. So this one has a pivot 1, and there's zeros everywhere else. The second column also has zeros everywhere else. And the first column has a 1, zeros everywhere else. So this matrix is said to be in reduced row echelon form. If it's identity matrix, if A is identity matrix. In this case, AX equals B has a unique solution for X, and A inverse exists. So reducing the matrix tells us a lot of information. And you could play around with a website where you can construct some examples of matrices in reduced row echelon form if you click this link in the notes. So here's the example. We start with a system of equations, and the coefficients are 4, 1, minus 1, 4, 1, minus 1, equals 11, equals 11. Minus 3 minus 1, 4 equals minus 12. Minus 2, 1, 3 is minus 5. So we could start row reducing using the elementary row operations we introduced last time. to get rid of non-zero entries, for example, in the bottom row, we can get rid of this entry, making it 0, by adding 2 times row 3 to row 1, minus 4 plus 4 is 0. And then if you add them, you should also get this. This is just algebra, and I don't want to spend too much time on this. You could check yourself. This is how the equation changes, and these equations are equivalent. If we undo what we did, so if we, let's see, we added 2 row 3 to row 1 to get this. So if we subtract row 1 from here and divide by 2, we'll get back the old row 3 that we had. So this is equivalent. Algebraically, it's the same thing. Now we can also get rid of the minus 3 by adding 3/4 row 1 to row 2 and putting it in row 2. And then I want to simplify a little bit, so I want to multiply row 2 by minus 4. So everywhere minus 4. Now, if I do row 3 minus 3 row 2 and put it into row 3, this matrix is now in row echelon form. And let's go back. What did that mean? All rows having 0 entries are at the bottom. There are no rows having all 0 entries, so that doesn't apply. It's satisfied. The leading entry, the pivot of each row, is to the right of the pivots of every other row. So this pivot is to the right of the 1 and the 4. And this pivot 1 is to the right of the 4. So this is in row echelon form. In fact, all of these matrices are in row echelon form because they all satisfy this. But now let's get to reduced row echelon form. So now if we have leading 1s instead of a 44, let me point out, actually, this is an upper triangular matrix, which we said is easy to solve because this system is easy to solve now. We get Z, we plug it in, we get Y, we plug it in. But this is what the process looks like in terms of matrices. So in terms of matrices, solving for Z looks like we get a leading 1 in the third row. Then we add 13 of the third row to the second row to reduce the second row as much as possible. And then we could subtract row 2 and add row 3 to get zeros in the first row. And then we divide everything by 4. Now this is in reduced row echelon form because not only do we have the pivots are to the right of each other going down, but also the pivots are all equal to 1, and everywhere else in the column we have 0. So the columns are only zeros and 1, and the pivots are all 1. So this is the only one that's reduced row echelon form. And this one completely tells us what the solutions are. X is 2, Y is 2, Z is minus 1. So that's why reduced row echelon form is useful. It's just a linear algebra way with matrices to get what the solution of your equation is. So this is an example of Gaussian elimination. And we used elementary row operations to get to the matrix AB, where B was 2, 2, minus 1, the column. So here I wrote row transpose, which is the same as the column, because I don't want a big space in the middle of my line to go up and down. So it's easier sometimes to write the row transpose. So this orange one was REF, and we went over how it was REF. You could read this in the notes to remind yourself why. And this matrix was RREF because of the pivots being 1 and because each of the columns had 0. So here's some examples of more matrices in RREF. Here's a 2 by 3 matrix. It doesn't need to be an augmented matrix. We just need leading 1s. We need zeros in the columns where there are these pivots, leading 1s. And we need all 0 rows to be at the bottom. And we need the pivots to be to the right of each other going top to bottom. So this is in our REF. And notice that we still have a 3, 2, so not all columns have zeros. only the ones with pivots. So this is matrix 1. We'll refer back to it later. Here is another one in RREF. The pivot is all the way to the right side. And if we were to solve a system where this was a 3 by 3 matrix A and this was B, then we would get 0 equals 1. And this would have no solution. And putting the matrix or the system into reduced row echelon form shows us right away that there's no solution. But abstractly, this is just a matrix in RREF and doesn't tell us anything unless we apply it to a system of equations. Another matrix in RREF, actually with 0 row. So now we finally have a matrix where we have an all 0 row. It's at the bottom, as REF wants. We have pivots in every row going left to right below each other. All the pivots are 1, and all the entries with pivots in the columns have zeros everywhere else. This column has no pivot. It could have any numbers we want, and this corresponds to a solution. It's a unique solution to a system with 3 unknowns and 4 equations, and those 4 equations happen to be consistent despite having more equations than unknowns. So it has a unique solution here too. Here is a 2 by 4 matrix, which could represent a system with 3 unknowns and 2 equations. And if it does, we see it's an REF, and we get a unique solution for Z. But x plus 3y equals 2, so we get infinitely many solutions. Plug in any y into x is 2 minus 3y, and that gives a solution for x. So there's infinitely many solutions. Let's talk briefly about homogeneous and non-homogeneous systems. So in the table, we saw a system of equations with 3 equations and 3 unknowns of the form ax equals b. B was not 0, but if it was 0, we would call ax equals 0 a homogeneous system of equations. And if b is not 0, it's called non-homogeneous. Since b was not 0 at any step of our REF or our REF process of the Gaussian elimination, the system ax equals b is a non-homogeneous system. So if you're homogeneous, you stay homogeneous always. If you're non-homogeneous, if you are an interesting system, you will always be non-homogeneous. Here's an example of a system that here's an example of a system where, well, I was thinking of how we can reduce a non-homogeneous system to a homogeneous one and see if it's possible. It actually shouldn't be possible at any step. So homogeneous, non-homogeneous shouldn't depend on Gaussian elimination that you do. So you could try and find out about that by doing an example. So these are well defined, independent of any kind of elementary row operations you do. Let's talk a little bit more about the vector space structure of homogeneous systems. So homogeneous systems are very interesting and very useful if you're solving differential equations or other systems. So if AX is 0 and BX is 0, where A and B are matrices of the same size, then A plus BX is also 0 because we can distribute X, and now AX is 0 and BX is 0. So if I add these matrices together, I still get 0. In fact, if I take a linear combination of A and B, I still get 0 as well. So if X is a solution to AX is 0 and BX is 0, it's also a solution to a linear combination of A and B, X equals 0. So linear combinations satisfy this. Also, if AX equals B and CX equals 0 for the same X, A plus CX, well, AX becomes B, but CX becomes 0, so this is still equal to B. So a plus cx equals b also if ax is b and cx is 0. And more generally, a plus acx equals b as well. So if you take differential equations and you have some kind of non-homogeneous system, you'll see that part of solving it is finding all of these homogeneous solutions, because whenever ax is b is a solution and cx is 0 is a homogeneous solution, a plus any amount of c's will give also a non-homogeneous solution, or a solution to the non-homogeneous equation. But there's a problem if both of them are non-homogeneous, because if I try the same thing, ax plus cx will be b plus b, which is 2b, which is not equal to b in general. Here's another example. The matrices M satisfying mx equals 0 have an even more structure than preserving just the linear combinations above. If M is a square matrix, so I could multiply it by itself, then M to the kx, I can take out one of the M's and I get 0. And then anything times 0 is 0. So powers of mx are also 0. So that's pretty interesting. And this is only for square matrices. Um, Whenever mx equals 0 has a unique solution for x, the solution must be 0, because x is 0 is always a solution. And notice that for ax equals b, x is never a solution, or x is 0 is never a solution. So this is really important because it shows all homogeneous equations actually have solutions. This is not true for non-homogeneous equations. For example, this one. This has no solution because we have 0 equals 1 at the bottom. And it's not homogeneous because we have a 0, 1 on the right side instead of 0, 0. If it was 0, 0, we would have a solution. In fact, we'd have infinitely many solutions. X equals 0, and then y can be anything at all. Here's some more examples. Let's go back to the matrices we had when we were talking about RREF and make them into homogeneous equations. So in this case, we have AX is 0. It has a unique solution 0. In this example, we have infinitely many solutions. Little x is 0, little y is 0, and z can be anything. And this is consistent to what we saw before. If 0, 0, z1, 0, 0, z2 are solutions, then any linear combination is also a solution. The third component could be anything at all. Here's another one. It's a 4 by 3 matrix. In this case, x is 0, 0, 0 is the unique solution. We can pretty much ignore the bottom row. It does nothing. It gives no new information. So this is a 3 by 3 matrix. Identity x equals 0 will imply x is 0 is the unique solution. The 0 column vector. Here's another matrix, this 2 by 3, or sorry, 2 by 4 matrix, augmented matrix, which has a 2 by 3 on the left side. So it's 2 equations and 3 unknowns. The solution is not unique because we have more unknowns than equations, and we'll talk more about this later. This happens in general. If a homogeneous system has more unknowns than equations, it'll actually have infinitely many solutions, always. And in this case, the solution set is z equals 0 and x plus 3y is 0. And we can even write that as something like this. This is what x is for any y. This will be a solution. Let's talk about a theorem that summarizes some of the patterns that we've seen. So the number of pivots of a matrix can be referred to as the rank of the matrix. And rank has many definitions, but this is one equivalent definition. So we're going to use rank of A to mean the number of pivots of A when we reduce A to RREF. Rank A is actually well defined. It doesn't depend on what elementary row operations we do or how we do them in what order. the rank is well defined. And in fact, our REF of a matrix is well defined as well. REF is not. Since we saw all of these orange matrices were in our REF, but only the blue one, or in REF, but only the blue one was reduced row echelon form. So row echelon form is not unique. Reduced row echelon form actually is unique, which is nice. So here's a big theorem, Rouchet-Frobenius. Let AX's B be a system of linear equations where x's in Rn and A and B have coefficients in R. We could talk about the theorem if coefficients are not in R as well, but for now, just real numbers. The system has a solution if and only if the rank of A is the rank of AB. So if the number of pivots of A are the same as the number of pivots of AB. In this case, if A is m by n, just a reminder that A is m by n. If rank A is n, then the solution to AX's B is unique. And if rank of A is less than n, then AX's B has infinitely many solutions. So pay attention to the fact that n is the number of columns. So the theorem says something about the number of pivots versus the number of columns. If each column has a pivot, something good happens, assuming the conditions of the theorem are satisfied. If each column has a pivot, we get a unique solution. Otherwise, there are less pivots than columns, and we get infinitely many solutions to AX equals B. If B equals 0, then A and A0 always have the same number of pivots. So if we have a homogeneous equation, then the conditions of the theorem are always satisfied, and that's really nice. So if we go back to matrices 6 and 8, where the number of pivots are 2 and 3, they equal the number of columns in those cases. So here's matrix 6. It has the unique solution 0, 0. So same number of pivots as there are columns of A. So sorry, I mean, this has the same number of pivots as this big thing. They both have 2 pivots. So the theorem applies. And here's a unique solution because the rank is equal to the number of columns of A. This one, there were 2 pivots, but 3 columns. The rank is 2 for both A and AB. The rank is 2, which is less than 3, and so we get infinitely many solutions. Here, the rank is 3 for A and AB, because homogeneous solution will always have the same number of pivots for A and the augmented matrix AB. So the rank is 3 for both of them, theorem applies, and A has 3 columns, so we get a unique solution. And then this other example we had, there are 2 pivots, but 3 columns. And so the theorem guarantees infinitely many solutions. So if B is not 0, as in this matrix 5 up here, AB has 2 pivots while A has only 1 pivot. So the theorem tells us that there's no solutions. Because this has 2 pivots, this has 1 pivot. So the theorem applies in a different way. The system doesn't have solutions. Because 0 equals 1 down here, right? If we have a different number of pivots, we have 0 equals 1 somewhere, which means no solutions. Let's talk a little bit more about linear algebra theory. So if A is an m by n matrix, we say X's B is underdetermined, or A is underdetermined, if m is less than n. So if there are less equations than unknowns. What that usually means is there isn't enough information to obtain a unique solution. On the other hand, we say X's B is overdetermined or an overdetermined system if m is greater than n. So there are more equations than unknowns, and therefore too many constraints to obtain a solution. Of course, we can just have the same equation repeated m times, like x plus y plus z equals 1, x plus y plus z equals 1. Then the system will have infinitely many solutions, despite being called overdetermined. So similarly, an underdetermined system can have contradictory equations, like x plus y plus z is 1, x plus y plus z is 2, and could have no solutions. But notice with a homogeneous system, this never happens. It's an important fact that the rank of A is actually less than or equal to the minimum of the number of columns and the number of rows. So here's a proof sketch. Assume without loss of generality, we'll come back here, that m is greater than n. So there are more equations than unknowns. Then there are m rows and n columns. And when we row reduce, at most n rows can have pivots, as we saw above. It's possible that less than n rows have pivots. So in this case, the rank is less than or equal to n, right? If less than n rows have pivots or exactly n rows have pivots. We can't have more than n rows having pivots because there's only n rows. If A is an RREF, we could perform row operations on A transpose to make A transpose an RREF. Here's how we can think about it. So if A is in reduced to echelon form, the rows of A are already in a form where each pivot is 1, and the pivots appear in a staircase pattern from left to right. When you take the transpose of A, the rows of A becomes the column of A transpose. So the structure of pivots from A now appears entries in the columns of A transpose. So A transpose has a 1 on the top of its columns that are higher up than the ones below. Instead of being to the right, they are now above or below. However, we might have a bunch of terms in the bottom rows that are not equal to 1. For example, if we transpose, if we transpose this one, then we get 1, 0, 0, 1, 3, 2. So we get some stuff that is not 0, but then we can row reduce it to have two pivots just like A did. This one as well, if we transpose, then we can row reduce and have it become a matrix with two pivots, just like the old matrix we had. All right. All the ones that appeared in A still appear in A transpose. Nothing happened with those because of the conditions on RREF. No one pivot appeared in a column below another one pivot in the original one. And same thing in A transpose, once we row reduce, we still have that one left over. Try some examples to convince yourself. So if m is less than n, A transpose is n by m. And we saw in that case that rank A transpose is less than or equal to the number of variables in the system, if we consider this as a new system. Right, so here we had rank A is less than n, where n was the number of columns. Now the number of columns is m, and so this is guaranteed. Therefore, the rank of A is equal to the rank of A transpose because they have the same number of pivots by the discussion above. And that's less than or equal to the number of columns of A transpose, which is the minimum of m and n by assumption. In both cases, rank A is less than the minimum. So that's it. In the case of a homogeneous system, AX is 0 being underdetermined guarantees there are infinitely many solutions. As in this case, A satisfies rank A is less than this and satisfies the conditions of Rouchet-Frobenius to guarantee solutions since it's homogeneous. And the same theorem then guarantees infinitely many solutions in that case. If A is overdetermined, then rank A equals n because there are a bunch of equations of this form. which of course still have a solution where each one of them is zero, since homogeneous systems all have solutions. So rank is a very important concept, and it's usually taught together with the concept of nullity. And for that, we need to define linear independence of matrices, which is one of the most important concepts in linear algebra. So here it is. If x1 through xk are m by n matrices, we say that these are linearly independent if whenever you have a linear combination equals zero, that implies each AI must be zero. In particular, this definition applies to column vectors, row vectors, and any other commonly used matrices. You could take any dimensions you want. So for example, 1, 0, and 0, 1 are linearly independent. You could check that a times 1, 0 plus b times 0, 1 equals 0. Well, this is equal to ab. And to be the same vectors, you need to have the components be the same. So this implies a and b are both 0, which is exactly the definition of linear independence. Uh, each scalar must be equal to 0. Here is a more general example. If you have any n, the collection of n many n by 1 columns, called this, where ek, the entries are defined to be 1 if I is k and 0 otherwise. So this would be E1, and this would be E2 in R2. And E3 and R3 is just 1 in the third component. The column vectors are referred to as the standard basis of Rn, and these are actually really important. This is considered the nicest linearly independent set in Rn, although there's many other independent sets. Any collection of m by n matrices containing the zero matrix must be linearly dependent. Because, well, if one of them is zero, for example, x1, then for any scalar, if I multiply it by x1, I get 0. It's true for any a1. So it's not true that all coefficients must be 0 for a linear combination to equal 0. Therefore, this is not linearly independent, which we refer to as linearly dependent. So now that we know about linear independence, let's define nullity. The nullity of A is the number of linearly independent solutions to AX equals 0. Nullity is well defined. Despite there being multiple possible linearly independent sets of collections or sets of solutions to AX is 0, all of them have the same size. Here's one of the most important theorems in linear algebra, which we won't prove right now. But if A is m by n, then the rank of A plus the nullity of A equals n, the number of columns of A, no matter what matrix you have. So this is really interesting. Take some time to think about this. One can think of m by n matrices as functions from Rn to Rm, because A takes an n vector to an m vector. If we think of x in Rn and b is in Rm. So A takes x to something in Rm. So we could think of it as a function. It's a fact that A is injective or one-to-one if and only if the nullity of A is 0. Yeah. So Richet-Frobenius guarantees a unique solution whenever n is the rank A plus nullity A, which is the same as rank A, because A is injective. Right? If the nullity of A is 0, then n is equal to rank A already. And A is guaranteed to be injective by rank nullity theorem, or by this fact about injectivity. So otherwise, if you have AX is 0 and AY equals 0, then you could take linear combinations of X and Y and get infinitely many solutions. And here's some more examples considering different triangular matrices. And I'm just going to quickly go over these, and you can go over them more carefully yourself. So here's what we're going to do. We're going to consider AX is B, where A is m by n, x is n by 1, and b is m by 1. And A is a triangular matrix. So example 36 is an underdetermined upper triangular matrix. It's underdetermined because there's less equations than unknowns. So 5 unknowns, but only 3 equations. So there's infinitely many solutions where x1, x2, x3 can be written in terms of x4 and x5. We can actually solve this by augmenting this whole matrix, taking this 3 by 3 and this 3 by 3. Here we'll get identity once we row reduce, and here we get something, and here we get something else. And this will correspond to equations in x1, x2, x3, x4, x5, where x4 will be a function of x1, x2, x3, and x5 will be a function of x1, x2, x3. We'll see something like this below. I'm not going to do this one out explicitly, but it'll be similar to one we'll do below. In RREF, there's 3 pivots for A and also 3 for AB. So Rouchet-Frobenius applies in the sense that it guarantees solutions. And 3 is less than 5, so there's infinitely many solutions by the theorem without any kind of solution by hand. I guess you need to know what happens when you row reduce in order to just use the theorem. Here's an underdetermined lower triangular matrix. Here there's actually 3 so again, it's the same thing, 3 equations and 5 unknowns, but it's lower triangular, and so these are 0, and so x4 and x5 don't even appear in the equations. In this case, x1, x2, and x3 could be solved for uniquely in terms of numbers, and x4 and x5 could be anything. So there's infinitely many solutions because of x4 and x5 being anything. Here's an overdetermined upper triangular matrix. So there's 5 equations and 3 unknowns. In this case, the number of pivots AB depends on B4 and B5, right? If B4 and B5 are 0, then AB will still have 3 pivots, and these will be 0 rows. If B4 and B5 are not 0, we won't get 0 rows in both of them. We'll have one non-zero row. So we're going to have a problem. The system's not going to be consistent, and you'll have no solutions because the number of pivots will be different. Otherwise, if B4 and B5 are 0, there will be the same number of pivots, and we'll get a unique solution. Here's the most difficult case out of these, overdetermined and lower triangular. So we have 3 unknowns and 5 equations, and the number of pivots of AB actually depends on B4 and B5, or any other 2 of the variables, but B4 and B5 are easier. B4 and B5 depend on B1, B2, B3 in a way that depends on this matrix. So if either B4 or B5 do not depend on B1, B2, B3 in a specific way, if we just pick them arbitrarily, then AB will have 4 pivots, so the theorem won't apply. And again, in this case, the system is inconsistent and there are no solutions. Here's if we row reduce. So here I'm just doing everything by hand. If I divide this by 2, I get B1 over 2. If I now add 3 of those to B2, I get this. And if I look at this equation and I subtract the B1 over 2, and I add 4 times this, and then then I need to divide everything by 3. I forgot to divide by 3. Then I get solutions for X, Y, and Z. And then if I take B4 and I subtract off 2 of these rows, and I add 7 of these rows, and I subtract 3 of these, I get 0. And so I needed to divide by 3 here and divide by 3 here. But I hope the color coordination helps a little bit. From B5, I subtract 4 B1 over 2s. I subtract 5 whatever y is. and I add a z. Oh, sorry, that's divided by 3, not the other one. Um, so if I do this process, I get uh, solutions for B4 and B5 in terms of B1, B2, and B3. So this is the only way that this has solutions if B4 is this and if B5 is this. It doesn't matter what it is exactly. The point is it depends on B1, B2, B3. Um, the following amazing thing is true. AX equals B has a solution if and only if B is a linear combination of columns of A. This is true in general. And if A has M linearly independent columns, AX equals B has a unique solution since B is M by 1. This is true in examples 36 and 37, these overdetermined systems, but is not guaranteed in examples 38, 39 in the underdetermined systems. For example, we saw in 38, we had 3 linearly independent columns, and here we needed B4 and B5 to be 0 in order to get B1, B2, B3 as linear combinations of the columns of A. Yeah. All right. Thanks.